Hello and welcome to more 6.5 Theory B, the last theory bit of this chapter though. And we're going to take a look at calculations with sines, cosine, and tangents, trigonometry you can say, in 3D shapes. You can use Pythagoras' theorem. It's very funny because this is what they call it in the new version of Numbers in Space, but in version 10, which we did with you guys in second grade, they didn't call it Pythagoras' theorem, but they call it the Pythagorean theorem, right? Same thing. You can use Pythagoras' theorem to calculate the lengths of line segments in a cuboid. You do not need to know which angles are 90 degrees. You should use each face and each diagonal cross-section in a cuboid is a rectangle. So just to translate, ze zeggen eigenlijk dat elk vlak en elk doorsnede, diagonale doorsnede, in een balk een rechthoek is. En als je dat weet, dan weet je dat er ontzettend veel rechthoeken ontstaan. This diagonal cross-section, if you go from one point in the corner, one vertex to the other, I think in second grade we also call it diagonal planes. You should use the trigonometric ratio sine, cosine, and tangents to calculate angles. First, find a suitable right angle triangle or a suitable diagonal cross-section or diagonal plane. Then sketch the triangle or the section separately. This is very important. Really, sketching was already quite important in this paragraph, in this chapter actually. But here it's even going to be of even more importance. If I take a look at this, for example, and they already make it a bit easier by coloring this diagonal plane here, this cross section BCEH, in a slightly red tone, or pink or orange, whatever you call this, because that already gives us an overview of where we can find angle BEC. Angle BEC is this weird angle here, BEC. And it's already made a bit less abstract by drawing BCEH, because then you see, oh, it's actually an angle in that diagonal plane BCEH. Without that given, you will just say, oh, that's a strange thing in 3D, I cannot do that. Well, actually you can. It's just very important to find, if I have BEC, sorry, in which diagonal plane, in which diagonal cross section, in which flat rectangle does this angle occur. And of course we still have to use the ratios for that, but the first and most important part is finding that. The book says now, well, start by sketching that diagonal cross section. So in this case, EHBC, and they sketch it like this, and they say, well, this is the actual angle that we want to know. The only problem is, I only know one thing. I don't know this angle, and I only know, if I take a look at this from angle E, the opposite side of angle E. So I either should also know the hypotenuse, so I can use opposite and hypotenuse. I can use the sine here to calculate angle E, or I should know the adjacent sides, because then I can use the tangents. Luckily for us, it's quite, well, not yeah, I think easy if you practice this a lot, but it's quite, you can actually calculate EB quite quick, I should say, because EB is in face ABFE. So we're going to use Pythagoras' theorem, or Pythagorean theorem, to calculate BE in triangle ABE, or you can say in face ABFE, and in that is the triangle. We can do that by saying BE squared equals AB squared plus AE squared. We are maybe a bit more used to the other way around, right? Then we say AB squared plus AE squared is BE squared. Of course, it's the same. AB squared is 4 squared, that's 16. 2 squared is 4, so BE squared is 20, therefore BE is the root of 20. And now I know the actual length of BE. So now I cut back to my diagonal cross section, my diagonal plane, And we're now going to fill in BE is root 20. And because I now know the adjacent sides and the opposite sides, I can now use the correct trigonometric ratio. I already spoiled it a bit. If I know the opposite and the adjacent, I think we're going to use a tangent here, right? Tangent of angle BEC. And you say, sir, why do they notate this like this, by the way? Maybe you're not that used to notating like this. That means if I just say angle E, it's not very clear in 3D what they mean with that, right? So here they mean the angle if I go from point B to E to C, B to E to C, hey, then I have one angle. That's the angle that they want you to know. If I would just say angle E, yeah, what angle E? Angle E in AEF or angle A in FE in EFGH, right? That's why you notate it like this. So the tangent of angle BEC is BC divided by BE. Or you can say 3 divided by root 20. I don't want to know the tangent of that angle, I want to know that angle itself. So here, take the inverse tangent, you can say on both sides. Here, inverse tangent and tangent disappear, so I find angle BEC is the inverse tangent of 3 divided by root 20 is approximately 33.9 degrees. It's very important for you to sketch this kind of things. They just give you 3D thing yourself, right? You don't have to sketch that, but then sketch those so-called diagonal cross sections or diagonal planes, so you can then find which angles they are actually talking about. If you do not do that, it's a lot more difficult and a lot easier to make mistakes in calculations like this. And I think this can be rather abstract for some. And making sketches, it makes it less abstract and more visually understandable. And that's it, ladies and gentlemen. That was the last theory bit of 6.5. Hopefully you're able to complete all or at least most of the exercises from the project. If you have any questions left, feel free to of course ask them in the lesson. I wish you all good luck on completing your projects.